A soil mass is composed of small solid particles which we call the soil grains. These soil grains, when depositing in a soil mass, arranges themselves in a way that some amount of empty space is left between them. We call these spaces voids. And the property of the soil which permits the water or any liquid to flow through its voids is called permeability. Permeability is the ease with which water can flow through the soils. For many engineering projects, we need to know the permeability of the soil as it is very important engineering property. There are numerous methods through which we can measure the permeability of a soil in the field or of a representative sample in the laboratory. We have already discussed the laboratory methods. Permeability of the soil in its natural deposits is highly influenced by its natural structural factors such as non-homogeneity and stratification. So, it is not possible to take out a soil sample which may represent the true in situ structure of the soil to be used in the laboratory. Also, for coarse-grained soils in which permeability values are very significant, it is very difficult to obtain undisturbed sample. So, to deal with such problems and to obtain a near accurate value of permeability, we perform field test on the soil mass. Usually, pumping out test is conducted for the purpose. We perform these tests for large engineering projects because these tests are very expensive. Pervious soils in the ground are the reservoirs of the groundwater. Their voids work as a storage and passage for the water. Such an underground layer of permeable rock or unconsolidated material such as gravel, sand or silt is called an aquifer. It is a body of saturated rock through which water can easily move. The groundwater from the aquifer can be easily pumped out. In the nature, we usually encounter two kinds of aquifers. One is unconfined aquifer and another one is confined aquifer. Unconfined aquifer simply means an aquifer that does not have a confining layer between it and the ground surface. Water can flow directly between the surface and the saturated zone of the aquifer. An impervious layer may present under the aquifer but not above it. The water level in the unconfined aquifer remains at the atmospheric pressure. These aquifers are sometimes called water table aquifers because their upper boundary is the water table. But sometimes this porous water holding layer is confined or sandwiched between two impervious layers of soil, and the aquifer is bounded at the top and bottom by relatively impermeable strata. These kind of aquifers are called confined aquifers. In such aquifers, water cannot enter or leave by vertical flow because of these impermeable soil layers. These impervious layers of soil are called aquicludes, and these are often made up of clay soils. Under such conditions, water may also be present in the pressurized state. For these two cases, permeability calculations will be slightly different. In this video, we will discuss only the permeability of unconfined aquifer. And for that, we perform pumping out method. Pumping out method involves making a well into the ground that reaches the aquifer and penetrates it throughout its whole thickness. It is important that well penetrates the entire thickness of aquifer. It is called test well. Water is pumped out through this well, and as a result, groundwater table lowers. The profile of the water table that may be horizontal at the beginning now acquires this kind of shape. That is called cone of depression. Pumping out test influence a large area around the pumping well, and that we can observe by making two observation wells at some distance from the test well. We can measure the difference of water levels in them before and after the water has been pumped out of the test well. When the water is pumped out, a hydraulic gradient is formed inside the soil mass because of the water profile generated. The height of the water table at any point indicates the hydraulic head or hydraulic energy of the water at that point. We know water flows from high hydraulic head to low hydraulic head. The water level in the well is lower than its surroundings and has lower head. So, water will flow from all directions of high head into the well of low head. If we imagine it in 3D, then we can see the flow is radially inward from all directions. Hence, when we pump out the water from the well, the water in the aquifers moves towards the well and it starts refilling it. But still, we continue the pumping of water till the steady state of flow is reached. The steady state of flow is reached when the amount of water pumping out from the well becomes equal to the amount of water refilling the well. So, rate of water radially crossing in this cylindrical surface is equal to the rate of water entering into the well. And that is also equal to the rate of inflow water from this cylindrical surface. At this state, water level in the well will not change. In such a state, the drawdown curve becomes constant and the water level in the observation wells is also becomes constant. So, let at this steady state, the height of the water level in the first observation well is Z1 and it is at a distance of R1 from the center of the test well. Similarly, the height of the water level in the second observation well is Z2 and it is at a distance of R2. We assume that the flow in the soil voids is laminar, so we can apply Darcy's law for this situation. According to Darcy's law, discharge rate from the well is equal to the permeability of the soil multiplied by the area through which water is percolating multiplied by the hydraulic gradient which is causing the flow. We can see the hydraulic gradient has a curved profile. It is not constant. So, let's assume that at some distance r from the center of the well, water level is z. And at a little distance dr away, the height of the water level increases by dz height. For such a short distance, we can consider the hydraulic gradient as a constant, and that will be equal to the change in the head divided by the distance over which the change occurs. The area through which the water is percolating by this hydraulic gradient is this cylindrical area of radius r and height z. Surface area of this cylindrical surface is 2 pi r z. Rearrange it like this. Now we can integrate it from our observation of water level in the well, which was at R1 distance from the test well was Z1, and level in the well which was at R2 distance was Z2. After integrating and applying limits, we can find the equation of permeability of the soil. We should keep in mind that in obtaining this value of permeability of the soil, we have assumed certain things. First, we assumed that the flow is laminar and steady inside the soil. Second, we assumed that the soil mass is isotropic and homogeneous. Third, we assumed that our test well penetrates the entire thickness of aquifer. And with that, we assumed that the flow of water towards the test well is only radial and horizontal, and water does not enter the well from the bottom. Write down daily learnings or express your creative self in E's homemade diaries. Buy them at Professoro or Amazon. Link is in the description. Take a look at an example of pumping out field test of unconfined aquifer on E's website, and also read the test on elementaryengineeringlibrary.com. Link can be found in the description. Thank you.